Well, good morning. Today we will talk something about FPGA, an introduction to FPGA. First, look what FPGA are. Now, FPGA stands for Field Programmable Gate Arrays. What an FPGA is? An FPGA is basically an integrated circuit which is configurable, that is programmable. What is programmable about FPGA? We will talk it about later. Now, what are the programmable components of FPGA? Are the logic blocks and the interconnects. There are some logic blocks in FPGA, and the interconnections between the logic blocks, those are the main configurable component of FPGA. Now, the term field programmable. Why the term field comes? The field stands for programming in the field, that is, the device function can be modified or configured or programmed in the lab or at the site where the device is installed. Okay, means you have this FPGA, sometimes you can use it at the site to perform say addition, at sometimes say you can use it for multiplication and so on. So, why it is called field programmable? Because we can modify the function in the lab itself. Now, FPGA is an inexpensive and easy realization platform of logic networks. Means you can use this can be used in the academics or by the students to verify the logic networks in hardware. It is as simple as software. FPGA generally contains some programmable logic devices, some logic gates such as your XOR, NAND, such gates are present. There are some RAMs and some other hardware components such as your DCM, that is the clock managers, and so on. Now, in an FPGA contains a layout of a unit which is repeated in a matrix form. Suppose this is an FPGA core, there is a certain unit which is repeated in a matrix form. For the user can configure the function of each logic block, the input output ports, and the interconnections between the logic blocks and the input output. Now, today there are many vendors which provide FPGA such as Xilinx, Actel, Altera. These vendors provide different types of FPGA boards. They differ in the programmability it provides, means the way user can program it, means implementing the programmability. They differ in the interconnection arrangement. They differ in the interconnection arrangement between the logic blocks and the basic functionality of the logic block. Now, what does an FPGA block? We are talking about logic blocks in FPGA. What does the logic block in FPGA contains? Generally, a logic block of an FPGA consists of LUT, that stands for lookup table. What is a lookup table? Suppose we use a 2-input lookup table, for example. suppose there are two variables a and b, and corresponding to them there is a function. Now, what are the possible combinations that can appear is this. Suppose the function corresponding to them is this. Now, what does a lookup table contains is this function 1 0 1 0, fine, and a and b acts as a memory address pointer. Now, when a is 0, b is 0, the first value is selected. When a is 0, b is 1, the second value is selected. So, this is what an lookup table is. Now, a basic FPGA combinational block consists of a lookup table. We have shown here a 3 input, which is generally actually is 4 input. There is a mux and there is a storage element. Now, when ABC appears, it selects a particular functional value which can be available at the output of the logic block, or it can be stored in a storage element for subsequent use, or this mux can make available another value at its output. This will depend on the function which we want to realize on the FPGA. Now, an example of an lookup table again. Suppose we have to realize a function a and b ORed with complement of c. So, what is the required function? This is the required function a b ANDed and ORed with complement of c. The truth table is something like this. So, what we have in the lookup table is an SRAM cells. There could be some other types of cells. So, we can use Antifuse and all those techniques, we will talk a little bit later. Suppose we have a SRAM, means static random access memory. The functional output is stored in this SRAM. All these values are fed to a 8:1 mux. The mux select line are ABC. When ABC is 0 0 0, then the first line is available at the output. When ABC is 0 1 1, then the fourth value is available at the output. So, in this way the function y is realized. Now, what is programmability in FPGA? There are actually 3 programming methods. One is SRAM based, another is Antifuse technology, and another is EPROM and EEPROM. Now, SRAM based programmability method is used by the Xilinx FPGA and the Altera based FPGAs, whereas the Antifuse technology is found in the FPGAs provided by Actel and QuickLogic. EPROM, and these are not very commonly seen. We will mainly concentrate on SRAM, and we will talk some little about Antifuse technology. Now, SRAM based programming. Now, in FPGA, now let us look at the basic FPGA architecture. Now, what does an FPGA architecture contains? Basically, we talk that there are some combinational logic blocks. This contains the logic block, which this one. This is the logic block. This is actually your this block. This is actually your this block. This is the logic block. This is actually your logic block. There are some input output ports that are programmable, and there are some interconnections that are also programmable. Now, these programmable interconnections, these interconnections are actually programmable. So, what does programming here means? We will program these interconnections. The main FPGA connections are what we found in FPGA are pass transistors, transmission gates, and multiplexers. Now, how do interconnection takes place? Suppose there is a these interconnects, these are interconnect lines, these are vertical interconnect lines and these are horizontal interconnect lines. Now, we have to connect this line with this line. What we have is we do not have any physical connection at this point actually. What we have a MOS here and an SRAM here. We can SRAM cell rather. Now, what we can do, we can program this SRAM cell to have 0 or 1. When it is 1, this creates a connection between these two lines. When it is 0, this connection is open. So, what is there is actually making or breaking of cross point connection. These are cross point. We are either making the connection or breaking the connection, and define the function of the logic blocks. We will see it in a while, how function of logic blocks is programmed. Now, here for example, now suppose this is a line. Suppose we have to, sometimes we have to make the output high impedance state. So, this is a SRAM cell, we will put a 0 there. Suppose we have to connect these two lines, this first line and the second line, then we will put a 1 here. Similarly, a transmission gate, again similarly a transmission gate can be programmed using a SRAM. Similarly, suppose we have require actually this output here, this output, then what we will program ABC, we will program ABC to 0 1 0. Okay. So, what is there? These are actually some SRAM cells which will be some values will be put there. Okay, and corresponding function will be available here. Fine, which is shown in this multiplexer. Suppose this is a 4:1 mux. Now, these two are the SRAM cells which will select the line. Okay. So, this is all what is programming in FPGA is. Similarly, suppose this is the logic block. Suppose sometimes we require the present, now this line gives the present value of the function, at this line gives the previous, means the previous state. Okay. Now, this SRAM can be programmed to take the present value or the stored value. Okay. Now, how is this SRAM based programming takes place? Now, we say that there are some IOBs, input output blocks. There are two pins which are called the configurable, I think configurable pins, which are used to program the SRAM cells. Now, these SRAM cells are basically arranged like a single shift register. Okay. The configurable, now that when you implement a logic into a device specific, means into an FPGA device, what it generates? It generates a configuration or bit file. Okay. Means it contains some bit streams. These bit streams are actually serially loaded into this shift, into this SRAM cells. Okay. Now this is all about SRAM based programming. Another type of programming that we have is the antifuse technology. Now antifuse technology is actually a one time programming technique, means you have programmed it once and it's over, you cannot reprogram it. So what an antifuse is? Antifuse is a link in configurable paths. Suppose this is a path, there is an antifuse here. In an unprogrammed state, this antifuse has a very high resistance, hence it models as an open circuit. What physically we have, suppose this is the metal 1, this is the metal 2, and in physical layer this is the metal 1 and this is the metal 2. This is actually your antifuse, which is basically non-conducting silicon, you can say. Okay. This is an oxide layer. Now when a high voltage is applied to this antifuse and a connection is built between these two metals, because that is the silicon, non-conducting silicon becomes conducting due to high voltage applications. The conducting properties of the silicon actually changes. This is something at the device level, we will not talk much about this. So once this is done, you cannot return to this state. Okay, so it cannot be reprogrammed. Fine. Now about FPGAs, we talked that FPGAs are generally programmable. Now in antifuse technology, we are saying that it is not reprogrammable. Means once you have programmed it, you cannot reprogram it. Why it is so? We have said that FPGAs are programmable. You have downloaded one program into it, you can again download some program into it. In antifuse, we are saying that once you have programmed it, you cannot reprogram it. So this is actually violating the basic theory of the FPGAs, right? Now antifuse technology, now here comes the comparison between the antifuse technology and the SRAM. Antifuse is there. Why it is there? We should know why antifuse is there. Now, what SRAM is? These are actually memory elements. You can say that these are D flip-flops or something like that. So in the FPGA, they are taking some extra area, which is rather not a part of our logic. It is blocking some area. In antifuse, what is there? There is just a silicon, just a small. It also occupies the area, but smaller with comparison to SRAM. What we have? We have a silicon crystal like there. Okay, so it occupies a much lesser area. Secondly, here the delays are very high. These are comparably high speed. Okay, so we can say that antifuse have some advantages over SRAM. Now we have to find some applications where once you have programmed an FPGA, you do not require reprogramming it. So some vendors, suppose there is a system, okay, whose functionality is fixed and FPGA is required that will connect this is an FPGA. Suppose this is a microprocessor. Suppose this is a DSP processor. Okay, the functionality of FPGA is to synchronize, interface these two blocks. So its function is fixed. Okay, you need not reprogram it here, right? But it has to satisfy the speed, the data speed between these two. In such conditions where we require dedicated FPGA, means its functions is fixed, we will go for antifuse technology. Am I clear? Okay, right. Now we will look into one of the vendors, Xilinx. Now now before going to it, we have to look into something about the in programmability. Now we have seen that the interconnect lines are between beside the CLBs there are some interconnect lines. These interconnect lines are pre-laid. Obviously, these are pre-laid, means before programming these are laid vertically and horizontally. Okay. At the cross point, we generally have switch matrix. Okay, what does this switch matrix does? It connects the lines to the input output of logic blocks. Suppose this is a logic block. Okay, it is connected to some other logic block. These outputs, now these are also configurable. Okay, now this switch matrix contains a set of multiplexers where an incoming line can be connected to outgoing line. Suppose this is an incoming line, this has to be connected to say this third line, then there are multiplexers that will be programmed. Okay, the path will be set. Fine. Now we will talk about the Xilinx specifics. Now Xilinx provide many FPGAs that differ in the complexity in the terms of number of CLBs rather. Okay, so what we Xilinx have, we have the Vertex 2 FPGA, the Spartan 3 FPGA, but at the base all the FPGAs contains CLBs. CLB stands for configurable logic blocks. There are some IOBs. IOB stands for input output blocks. PI stands for programmable interconnects. There are some RAM blocks and there are some other resources such as buffers, global clock buffers. Then you have your some dedicated multipliers are there. Today's we can find some dedicated multipliers. Okay. Now let's look into the Vertex 2. What we have at the outer sections, we have the IOBs. Okay, here you can see there these are the configurable logic blocks. These are the configurable logic blocks. The white space between shown are the programmable interconnects. There are some RAM running vertically, the RAM blocks. Beside the RAM blocks there are some dedicated multipliers. Fine. Now talking about CLBs, basically the CLBs contains slices. Suppose this is a CLB configurable logic block, which it has two halves. Each half is called a slice. We are talking about Xilinx FPGAs. Okay, so each CLB contains two slices. Now we look into this slice. What does slice contains? Now the slice contains two 4-input function generators, carry logic and storage element. Now look into this vertex slice. Now what is there in a vertex slice? You see there are two LUT lookup tables. These are what? These are the function generators. See, there are 4 inputs. They are numbered 2. So there are two 4-input function generators. Now you can see here an AND gate. Okay, you can see here CY. Now this generates the carry logic. Suppose you have to implement an addition in this CLB, then this provides the carry logic. Okay. Now there are two storage elements. Okay. Suppose your output has to be saved for the next level of operation. Then these flip flops comes into play. Here you can see an XOR. Now what does this XOR performs is the addition. Sometimes where you need an addition, you will not go for a lookup table, you will just implement here. Now all these functionalities are selected by the mux provided in between. Fine. So there are two slices. Now, so each function generator output drives CLB output. Here this is the function generator, it drives the CLB output, or it drives the output of a input of a D flip flop. Okay. Now these two function generators can be combined to provide functions of 5 to 6 inputs. Now here we are confined that our function should be 4 input, not more than that. Suppose we require 5 to 6. There are some logics provided which uses these two LUTs to provide 5 to 6 input functions. Fine. Now talking about IOBs, the input output blocks. Now the input output blocks appears as a storage element. It either, now look here, suppose this is the input section, means your logic is in this portion. Okay, this is the pad, this is the connection to the outside. So you have to this line, you have to output it. Okay, you can output it through this mux, through this buffer. You can store this output in this flip flop and can output it through this mux. Fine. Similarly, for the input, you can, from this pad, the input can be stored through this buffer. It can be stored in this D flip flop, or it can directly be sent to the core of the FPGA. Okay. Now there are certain modes in which this IOB can work. That is the synchronous set mode, synchronous reset mode, asynchronous preset mode, asynchronous clear mode. We will not go into details into this. Now we talked about it, that each IOB can be programmed into input path or the output path. The input path, there are some buffers, those that routes the input signal directly to the core or via the flip flop. Similarly, the output path, there are some buffers which routes the output signal from the core to the outer world directly or through the D flip flop. Okay. Now we talked that there are some RAM blocks. These RAM blocks, we know that were organized in columns. Why RAM is required? To store some intermediate data. There are programmable routing. Now adjacent to each CLB, this is in context of vertex 2, adjacent to each CLB we have a GRM. GRM stands for general routing matrix, which is basically, we talked about switch matrix, and it connects the CLBs. Resources are rather your CLBs, RAM, multipliers. So this GRM interconnects these resources. Now beside this, there are some arithmetic resources such as adders, counters and multipliers. Why it is required? It is to speed up an arithmetic operation, because nowadays FPGA has to compete with ASIC. So, the main reason the main field of competition is your speed. So, FPGA has to reach not fully, but some portion, some part of the speed achieved by the ASICs. So, these are all intelligence that the FPGAs nowadays have to speed up the functionality. Now, we see that there are some dedicated carry logic and XOR to function to implement the addition. Now, where do FPGAs lies? An IC can be programmable or one-time programmable, means we have learned about ASICs. There are some programmable logic devices. These are generally simple programmable logic and complex programmable logic. Now, these PLDs are highly configurable. Okay, you can every time you can configure it. You can use it to implement your functions. The design time is fast. In a day or two, you can implement a function, but they can't support complex logics. Suppose you have a huge logic, but they cannot be implemented on PLDs, whether it be CPLD. At the other end of the spectrum, we have the gate arrays, ASICs, standard cells, full custom. Now, these ASICs provide no reconfiguration. The design is highly time consuming. The design is expensive and but supports complex function. Now, where FPGA sits? FPGA sits in between these two extremities of the designs, digital designs. What it has some functionality of the PLDs, it has some good features of the ASIC, right? Now, FPGA generic design flow, how we design when we talk about FPGA. At the first level, we have the design entry, means we create our design. We can create our design using schematic. There are some schematic where you have provided with AND gates, XOR gates. You can design with these are in schematic, or you can write your own HDL. Okay. Now, once you have created your design, you have to implement it. What does implementation means? Means given an HDL, you have to mold it into a language, we will not say language, into something that FPGA can use. Okay, means we are implementing our HDL to FPGA. What does this contain? This contain partitioning, place and route. Now, what is this? What happens in partitioning? Suppose you have an HDL. Okay, this is your HDL block, whether Verilog or VHDL. Now, in the FPGA, what we have? We have the CLBs, right? These CLBs are 4 input or 4 inputs. Say consider these are 4 inputs. Okay, now we have to partition our program into logic blocks which are 4 inputs. Clear? So, this is what happens in partitioning. Now, the next step is place. Now, suppose we have 3 logic blocks. Now, there are some millions of CLBs nowadays available. Now, which CLBs will you choose? Will you choose these 3 or these 3? Now, these decisions are actually taken in placing. Okay. The next part is your routing. Now, suppose in the place you have selected that these CLBs will be used to implement our logic functions. Now, the routing will find the interconnects. How will they be interconnected? The paths. Okay. Now at the same time, when this design flow is going on, at the same time you should have to, at the every level, you should go on verifying your design at the every level. Suppose you can use a simulator at the design entry level, which are provided by your model sims, model sim, you know model sim, I hope. Okay, or check the operation after loading. You have seen this somewhere, that operation of a FPGA after loading. Where? Yeah, that the logic analyzer. It was the functionality, the timing parameters were all tested after loading. Now, as I said, the combinational logic must be covered by 4 input, 1 output gates. Now, this is what actually happens in translation. Okay, means all your combinational logic should be converted into 4 input, 1 output gates. Not gates, we can say it as logic blocks. Okay, the flip flop from the circuit must map to the FPGA flip flop. Okay, suppose we require a 4 flip flops, right? In a CLB, we have only 2 flip flops. Okay, this means in under such case, we have to use 2 CLBs, right? Now the placement generally attempts at wiring minimization. Okay, because if wiring increases, then delay increases, then speed decreases. Okay, so these all decisions are taken at the placement. Now, an introduction to Xilinx ISE. What is this? Is a tool provided by Xilinx to configure FPGA provided by Xilinx. Fine. So, Xilinx ISE is a tool to configure the FPGAs provided by the Xilinx. Now, what Xilinx ISE is actually is an integrated software environment. Why it is called so? Because it is an integrated collection of tools accessible to GUI. Fine. Now, in the ASIC flow, you have seen excuse me, at the design level you have to use one tool, then in the synthesis you have to use another tool, at the back end you have to use a plethora of tools. Now what does ISE does is brings all these tools at the same place, okay, and provide it through a GUI. So it is extremely user friendly. Fine. Now what are the tools? The tools are XST, that is Xilinx synthesis tool, the pace, code generator, constraint editor, impact. These are all the tools. If possible, we can look into it in lab sometimes. Okay. Now at the design entry, what we provide to ISE? To the ISE, we can write the Verilog file or VHDL file or the schematic file. Okay. Now the synthesis is done by Xilinx synthesis tool. What it does? It produces a synthesis. We have seen what it does. It produces a netlist file starting from an HDL or a schematic description. So what a XST has? It takes .v, .vhd, .sch files and convert it into .ngc file. What is ngc file? The netlist file. Clear? Now after synthesis, we go for translate. Now translate is done by a tool called ngd build. Okay. What it does? It reads all the input design netlists. Suppose you have designed a mux somewhere. Okay, you have designed an adder. In another function, you have used those mux. You have just as function calling. You have used these mux and the adders. Okay. Now what translation happens, it reads all the input designs, okay, and then writes the result into a single merged file that describes the logic and constraints, okay, just as a flattening. Just read this means just it links all the logic files. So what translate gets .ngc from the XST, means the synthesis tool, and gives .ngd file. What is ngd? ngd is native generic database file. It describes the logic design reduced to Xilinx primitives. Okay, now we are going to the board, okay, towards the device. So ngd file describes the logic design reduced to Xilinx primitives. Now after translation comes the mapping. Now what happens in mapping? Mapping maps the logic on a device component. Okay, given a device, it maps the translated logic to this device. What it does, it takes the netlist, group the logic elements into CLBs and IOBs. Okay, now whatever information about this device, CLBs it has, it does here, it is done here. What it generates? It generates the NCD file and the PCF file. What is NCD? Native circuit description file. Now what does this NCD file contains? It contains the physical circuit descriptions, means interconnection between the CLBs, means the which CLBs are used, which IOBs are used, description of the input design as applied to a specific device. Now we have this mapping is device dependent. Okay, if you are using Spartan 3, mapping will take place in a different way. If you are using Vertex 2 Pro, these are the device. If you are using Vertex 2 Pro, then mapping will take place in a different way. Okay, now mapping generates the NCD file and the PCF file, that is the physical constraint file. What is, as the name says, it contains the physical constraints. Okay, means these CLBs can be used, these CLBs cannot be used, it will increase the delay. All those constraints are stored in the physical constraint file. At the next, after mapping, we have the place and route. It determines the placement of the cells, means which cell will be mapped to which CLB, and the routing between the cells. Followed by place and route, we have the bit stream generation, that is actual configuration, means the bit stream that is sent to the FPGA are generated after the place and route. So what is a bit stream? A bit stream is a stream of data that contains the location information, means which CLB for the logic on a device. After this, after the bit stream has been generated, we go for configuration of the device. Okay, in this, the bit file is downloaded into the FPGA using, generally we go for a JTAG port. Okay, now the tools that are being used by the Xilinx ISE. For the synthesis or HDL compilation, it has the XST Xilinx synthesis tool. For the simulator, it has itself provides a simulator Xilinx ISE sim, or it can use the model sim provided by the Mentor Graphics. For using the code, some there is a tool called code generator, which is code generator and architectural wizard. Means suppose in a system you need an FFT, right? You will not go for an FFT, you will not build an FFT, you will not build an FFT. what does this code generator generates FFT. You will provide it how many points FFT, what should be the speed. Okay, now these code generator are also, this Xilinx ISE can use this code generator FFT. Similarly, you can FIFO. Okay, these are codes. It can use directly the codes. Okay, the user will not have to make an FFT, will not have make an FIFO. Fine. Now there is another tool, PACE, that is pin out and area constraint editor, that is given an FPGA. The user can specify that I will give the input from these 3 and take the output from these 2. Okay, so what is this? This is pin constraint. Okay, then the user may give, I will implement this logic into this area only. Okay, I will use this area for some other functions. Okay, so this area constraint and pin constraint is given through the PACE, the tool called PACE. Then implementation is done by translate, map and park, the tool of Xilinx itself, and then the device configuration is done by a tool called impact. All these tools can be accessed through the Xilinx ISE. Now an example. Now suppose you have to implement a modulo 4 counter. That is, suppose this is the initial state 0 0. Suppose if enable is 0, it will return to its own state. If enable is 1, it will move to the next state, and so on. If enable is 0, then it will return to the present state, or it will move to the next state. So depending on this state diagram, we can create a truth table. That is, suppose the present state is 0 0 is this, x1 and x2 is named as x1 and x2. Enable, and the next state is y1 and y2. When enable is 0, then the next state is same as the present state. When enable is 1, the system goes to the next state. Okay. Now you can implement it like this. Suppose you put the function corresponding to y1 into an SRAM cell, then y2 into this SRAM cell. Okay, use the mux, the select line en, then your x1 and x2. Visible en, x1 and x2, right? Now this is your next state. After passing through this element, this become the present state because after a delay. Now so this is again used to select the next state. Clear? Is it clear? Not clear? So this is the next state, this is the present state. Fine. So why FPGAs? We have ASICs, we have PLDs. Why we will go for FPGAs? Because it is inexpensive, easy to handle, means program, and the time to market is very less. Okay, for an ASIC, a design needs 6 months to more than 6 months. Okay, when you are going for an FPGA, you will require hardly a 1 month or so. Okay. Next is FPGA can be used as glue logic to help connect large ICs. Okay. Now, as I said earlier, suppose you have microprocessors, DSPs. Now you will not go for an IC. Suppose you use this microprocessor. Suppose you use the microprocessor from you use your 8085. Suppose you use DSP processor from TI. Okay, you will not go to make an ASIC to interconnect them, right? You will use here what? An FPGA, so that you can make your system, you can reduce the time to make your system. Okay, so what is this? This is a glue logic, means this logic is used to interconnect the large ICs, right? Now, these FPGAs can be used to generate global control signals such as your reset. Then the data formatting, means how data are passed from one block to another block, such as serial to parallel, right? Then FPGA reduces the system complexity and the manufacturing cost. How manufacturing cost is reduced? Now, there is a concept called NRE, cost. Okay, whenever you go for a design, you require tools, right? You buy the tools for a once. Okay, you go for fabrication, means you need the fab labs, right? So once you have these, you can tape out your logics, okay, your chips. Now these costs which are required for only once, okay, just as the initial stage of the design, these are called the NRE cost, that is non recurring cost, right? Now suppose we plot the volume of production, okay, and this is the cost. For ASIC, the NRE cost is quite huge. This is the NRE cost, right? Okay, before any production, the cost, its initial cost, right? This is very huge. For FPGA, it is much less, but when you go for high volume production, your ASIC will be a cheaper option. At high volume production, FPGA will be a costly affair. Okay, so you have to decide in which range you are operating. Are you going for a low volume production or a high volume production, right? Now, the density, that is gates per area of FPGAs continue to grow. Okay, we are having larger and larger number of CLBs on these FPGAs. Okay, now due to this, the FPGAs are competing with custom IC, means custom ASIC, for special processing functions, and even competes with microprocessors in dedicated applications. It is removing the DSPs now. Now DSPs are DSP processors. What is DSP? DSP processors. Okay, DSP processors are being removed by FPGAs. ASICs are now replaced by FPGAs. Right. Now coming on to the last slide, there are some comparisons. We will compare the performance, means in terms of speed, okay, the NRE cost, the unit cost, and the time to market. Now we know that ASIC has the maximum speed. Okay, microprocessors has the least speed. Why microprocessor has the least speed? Compare means least speed means lesser speed than ASIC. Yeah, dedicated. In between the ASIC and microprocessor lies the FPGA. So FPGA falls behind in performance with respect to ASIC, right? In case of NREs, as I said, ASIC has a maximum NRE cost. Microprocessor has the lowest NRE cost. FPGA sits in between. The unit cost, for unit cost, FPGA has the maximum unit cost. That's why, since the unit cost is maximum, when we go for high volume production, the cost for FPGA production shoots up, right? For unit cost, ASIC has the lowest cost, and time to market, obviously ASIC has the greatest time to market, and FPGA sits behind it, and microprocessor based designs are the least, takes least time for market. Okay, this is all about FPGAs. Okay, thank you.